our plan, which we don't always achieve, but we do try, is to have the homework due on Friday would use material up to Tuesday's lecture. That would be today's lecture, right? So I do know that we had some people look at the homework and like, I can't do that. And yes, that's fine. So, and I'd also, I assume, I know I talked to a handful of people who'd already started on homework 1. Yeah, this is not one of those do it Thursday night homeworks, just to let you know. I like to think of it, you want to savor it. Actually quite seriously, I do want to say that, for homework 1, it's pretty challenging. I mean, there are at least some parts that are actually quite challenging. And I'm sort of hoping you'd have the sense to not bang your head on a wall for several hours on one problem or something like that. And just at some point, just to walk away. That's totally okay to do, right? So, yeah, so that's it. And especially at this point in the class where this is just background material, it's completely and utterly unmotivated at this point. But what's going to happen is you will be using all of these things for the rest of the quarter. And so what's funny is I remember talking to people who said, I remember doing like homework 1 and homework 2 and having just no idea what was going on. And then by homework 8 and 9, when they've actually used it to, fit models or optimize, flow on some network or something like that, then they were like, okay, now I get it all. So anyway, so just that's sort of just the spirit. Let's see, any questions about last time? Otherwise, we'll continue on. May I remind you, this week is continuing our slog through the math. It will finish pretty much on Friday. So already next week, the sun is going to come out, and if you've survived, it'll start getting actually very interesting. So, okay, no questions? So in that case, what I'll do is let me just say, remind you where we were. Last time we talked about the idea of defining an inequality in terms of a cone, a proper cone, right? And so that's a general construction. The truth is we really mostly do this only with 2 specific cones. One is a non-negative orthant, and that allows us to compare 2 vectors. And basically one vector is less than another when element-wise one is the corresponding entries are less than the other. And the other one is the positive semi-definite cone, and that allows us to compare 2 symmetric matrices, right? And you say that one is bigger than another if the difference is positive semi-definite. And I'm presuming you've seen this somewhere. I don't think these shouldn't be completely brand new. So what I mentioned at the end of last time is something quite interesting, right? That the idea of when you generalize an inequality, just the fact that the symbol we're using and the name we're using, which is inequality, like all powerful notation, it should remind you of inequalities among real numbers, right? That's sort of the idea, right? I mean, it's the same way when you write down AX equals B, where that's a matrix equation, and somebody looks at it and said, I solved problems like that in 3rd grade. The response is, yeah, but that's a 2,000 by 1,000 matrix there, right? Or something like that, right? So it's the same idea. And the idea of, this generalization is that many things are true. Many things you know in the old context remain true, and some don't. If everything remained true, then it's really not even a generalization. It's just, you're just saying it now applies to more things, right? And so the main thing that you don't have when you are looking at vector inequalities is it's not a linear or total ordering. And what that means is you can have two things, and it is false that this one is less than that and the other way around. Now for real numbers, that's impossible, right? Because either one real number is either less than or equal to the other, or the other way around, period, right? And so that's called a linear or total ordering. And you don't have that with vectors, right? And this is kind of obvious. Actually, we're going to see later that this actually has a lot of interesting practical implications that we will get to. Okay, so one thing that happens then is, everyone knows what the minimum is, right, of a bunch of numbers. And by the way, I might as well mention it now. When you have an infinite set of numbers, the min is replaced with something called the infimum. If you know about this, that's fine. If you don't, think of it as the min. It is just the min, but it applies to infinite sets. Okay, so that's really pretty much all you need to know. Okay, so what happens with a vector here, when vector inequalities, is that the idea of min or infimum or minimum or maximum for that matter actually splits into two concepts which are very different. One is still called the minimum, and the other one is still called actually minimal. And so these are just two different ideas, right? And we'll see actually later that this is going to come up in all sorts of in various applications and be kind of interesting, right? So minimum means that it's a point in the set with the following property, that everything else in that set is comparable and larger than or equal to u with respect to that inequality. That's what minimum is, right? It's not hard to show that that there's a unique minimum. In other words, you can't have two different points which are both, well, before you show it, you'd have to say a minimum, and then after you show it, you're allowed to say the minimum. Okay? Then there's the idea of a minimal element, and a minimal element is one. Like here's an example. X2 is minimal for this set S2, and you'd say with respect to the non-negative orthant, right? And what that means is, very roughly speaking, it means that there's no point in this set here which is less than or equal to X2 except itself, right? And so that's sort of shown visually here, right? You can also see that all of these points are minimal. Everything on this line is minimal, okay? How about like a point there? It's not minimal, right? Because there would be points which are comparable, that are in the set comparable and less than or equal to, and not equal to that point. Okay, so that's one thing. And this you'll just have to go to a quiet place and think about this, and you'll get lots of chances throughout the course to get this straight. There's a question.
What the minimal would be with respect to a different cone?
Yes. So when we talk about minimum and minimal, it is always with respect to a specific cone. Yeah, no, then it would not be this, right? Like, so if I had a different cone, like, let me just draw down a different cone, right? In R2. This is in R2, right? So here's a different cone. Like, it's this little thing here. That's a cone, right? In R2. And then we could ask, is that point minimal with respect to that cone? Do you want to make a guess? Oh, it is. Yeah, because I'll just reproduce that set a bit here. It looks like this, right? This set looks kind of like that. Here's the point. And what you want to do is you want to look at all the points that are less than or equal to this point with respect to this cone. And that basically looks like this. Let's see if I can do this right. It's going to be all these points here, right? And then we want to intersect that set with the set S, which is here, right? And find out if the only point is this point. And it is. So it is. So with respect to that cone, that point X2 is still minimal. Right. Okay. Now we'll get to something called the separating hyperplane theorem. It's actually super famous. It looks kind of innocent. And you can actually make a reasonable argument that everything we're going to do is based only on this. So it's not bad to have like a single visual picture that tells you everything you need to know. And what it says is this. It says that if I have two convex sets, right, which do not intersect, that's what it means to be disjoint. So I have disjoint convex sets. Then it says, very roughly speaking, I can stick a hyperplane between. I can separate them by hyperplane, right? And you may have seen this in some machine learning class where you were talking about, two different sets of points being linearly separable. That's how people would say it there. If you haven't, that's fine too. But so this is the picture, right? If there's a set C and a set D, then there is some non-zero vector A and a number B, so that if A is pointing this way, it says that A, this half space here is everywhere where A transpose X is less than B, and C is entirely in that set. This half space here is everywhere where A transpose X is bigger than or equal to B over here, and D lies entirely in that set. Okay, so this is the idea. Now, right now, this has no. This doesn't have any the context or anything like that. But we'll see later. It's related to a lot of stuff we're going to see by about week 5, right? I mean, it is the basis, for example, of a lot of economics, like period, right? Because this is basically, you'll see later, this will correspond, you'll say something like, well, there's no arbitrage. And that's going to turn out to be a picture like this. I mean, not in 2 dimensions, but nevertheless, it's what it's going to be. So we'll see that stuff like this, although right now it has no context, it's going to come up over and over again. Okay. There's a gazillion variations on this, like, when is this true with these strict, when the inequalities are strict? And then you say they're strictly separated. And it gets complicated and all that sort of stuff. You would see maybe 1 or 2 variations in the book, but you actually don't even, I don't think you need to know them. You just need to have this picture in your head, right? Now, showing this is actually not too hard. We're not going to do it. I mean, it's sort of like an exercise, and we'll see things kind of more sophisticated anyway. So that's a separating hyperplane. Yes?
What does singleton mean?
Oh, a singleton. Yeah. Oh, by the way, great. Thank you for asking. Please ask about anything that's not clear. I try. But that is high BBC mathematics. It means a set with exactly one thing in it, right? So that's a singleton, and that's completely standard, right? So I mean, maybe not in different fields, but in high BBC math. That's why everyone should speak a little bit of fancy high BBC math. You should understand a little bit. You should recognize it and actually speak some, right? I mean, if you're accent free, that's awesome. Then you can, I don't know, then you can hang out with mathematicians or something. But I mean, if that's a good thing, I don't know. Anyway, okay. And there's variations on it. And this is an important concept. We'll get to this later as well. There's the supporting hyperplane theorem. And so first I have to say what a supporting hyperplane is. So supporting hyperplane is I have a set, doesn't have to be convex, and I have a point on the boundary of the set here, okay? And if you don't know what the boundary is, we could just take that to be a completely informal, your eyeball will tell you what's on the boundary, okay? So that's a point on the boundary. And then a supporting hyperplane is a hyperplane that, very roughly speaking, is tangent to the set here. And what it means is it passes through this point, but everything in this half space is not in this set. Or another way to say it is this hyperplane tells you that this set is in one of the half spaces, right? That's what it tells you, okay? That's the supporting hyperplane. And what it says is if you have a convex set, then exists a supporting hyperplane at every point, right? And that's not too, I mean, it's kind of intuitive that this would be the case. The picture would be something like this. Here's a convex set, C. And let's look at some boundary points. So if you take a point there, there is indeed a supporting hyperplane, and it's basically just it's tangent to this set, right? By the way, what happens if I go to a corner? Suppose there's a corner there. Let's talk about supporting hyperplanes. Are there some? Is there more than one? Precisely, that's it, right? So when you have a kink in a set, there's one. Is there a supporting hyperplane to this set at this point? No. So that's what it means. Yeah, is that there's no hyperplane at that point that supports it at that point and has the set on one side of it, right? But by the way, the converse is also true. If a set has a supporting hyperplane at every point of its boundary, then it's convex. But again, if you care about these things, that's fine. But it's a lot of it is just, I think you should think of this intuitively. And these things are just going to come up over and over in applications, which will be really cool. Okay. Next weird, totally non-motivated thing we're going to do this week is dual cones and generalized inequality. So the first is, so actually let me just start. Let me explain what this is a generalization of, right? So you may know in linear algebra, if that's a subspace, then you have V-perp. That's how you pronounce this, right? And that's the set of all x for which y transpose x equals 0 for all y in V, right? So that's it. So that's a useful concept. It's a set of all things orthogonal to everything in your subspace, right? So that's what, and it kind of means, it's also called the orthogonal complement is another name for this. It's got a bunch of names, okay? And you may even know how to, compute a basis for it if I gave you a basis for, like, let's say V or something, right? Okay, so this is the same concept, except now with inequalities. Makes it, in fact, that's in some sense, that's all we're doing mathematically, is we're doing linear algebra with asymmetries. So we replace equalities with inequalities. That's actually all we're doing, right? So, okay, so let's look at what it means to be a dual cone. All right, sorry that I switched X and Y, but over there and here, but that's fine. So let's actually just draw some pictures, because I think that's really the best way to understand this. Okay, so let me write down the definition. So we have it, which is K star equals, and I mean, it's perfectly okay for me not to do this to get it right. This is for all X in K. There you go. Okay? So it says you have to make a non-negative inner product with every entry of the cone. Cool? Okay. So I'll just do a couple, and then we quit, and I let you go off and do this yourself. All right? So let's write down some cones. Look, here's a cone. Ready? Hey, it's a singleton. There we go. So that's a cone. It's a stupid cone, but it's a cone. Now you tell me, what is the dual cone of this? What is it? R2. It's R2. Yeah, because we're doing this in R2, so I can draw it on the board, right? So it's actually everything, because actually it says, what are the set of vectors so that when you take an inner product with a zero vector, you're bigger than or equal to zero. The answer is like anything. Okay? So in this case, you would write it this way. This is R2, right? Which is a cone. R2 is a cone. It's silly. It's also subspace, but it's cone. Oh, by the way, this is something you're going to see that's kind of interesting. When you have a dual cone, if the cone itself is kind of small, that's as small as cones get, right? Then your dual cone is big, right? And you've seen things like this. This is like a conjugacy type thing, right? So you have this in Fourier transforms, right? I'll go into dialect if you don't mind, but if you have a signal that's like very time limited, then its Fourier transform is big old wide, right? And conversely, right? The other thing about conjugacy things is you have this general concept in math that if you do it twice, you get back to the original thing, right? Like if you have complex numbers, the conjugate of a conjugate is the number again, okay? Over here with subspaces, like I was talking before, if you have a subspace and you go v perp, then perp that. Now, of course, your head explodes, because if you think about what v perp is, someone says, what are you looking at? You go, oh, it's the set of all vectors that are orthogonal to all vectors that are orthogonal to all vectors in this subspace. Now, you can pretend you understand what I just said, but I don't. I didn't get it. And no human being could. I mean, well, maybe a few, but they're weird, right? And so I'm just saying, these things, but you start using powerful notation and you get used to these things, right? So what is the dual cone of R2, by the way? It's that, right? So the only vector that has a non-negative inner product with all vectors in R2 is 0. Hey, look at that. Funny about that. The conjugate, the dual of the dual is itself. Okay? So, and these are just like meta ideas that we're going to see in different points in the course. Okay, let me draw some non-silly ones. How about this? Here's a cone in R2. It's a ray. It's all non-negative multiples of a vector. This just goes off to infinity. That's a ray, it's called. Okay? What's the dual cone of it? How do we find out? How do we figure it out? Yeah.
Half space that it's orthogonal to?
Yeah. So before we just jump in, I mean, that's correct. But let's do the following. Let's first just ask whether a vector is in the dual cone. This is K right here, and I want to know if you're in K star. Well, so here's a vector. Is that in K star? It is. Yeah. Because basically, this thing, it has a non-negative inner product with everything on this ray. I mean, on the ray, it just scales it, right? So, okay, so that's in the dual cone. How about this guy over here? How about that point? Yeah? Okay. How about this point over here? No, doesn't work. Okay. And so, basically by doing a couple of these, you will quickly figure out that in fact, this is the dual cone. It's a half space. So you could say something fancy like the dual cone of a ray, the dual of a ray is a half space. And notice that has our small big concept embedded there. Like a ray is kind of a very small little baby sharp cone. And then a half space is pretty much as blunt as a cone as you can get. Well, you can have all of our two, but that's silly, right? So okay, everybody got this? So I think these are the pictures, you can talk to people you work with or something like, but some of these get complicated, and actually a lot of these things you actually have to show. And they're not totally straightforward. They involve Cauchy-Schwarz inequality or something like that. But, we could, and these are probably best done, in either homework exercises or something like that. But, the things you'd have to show. For example, let's say k equals r plus to the n, non-negative orthant. And when I say the dual of that turns out to be, well, let's just do it in R2. How about that? We'll do it in R2, and then that'll give you a visual on it, and then you'll know that it actually generalizes. So here's my cone K, right? And now I just ask questions like, who's in the dual cone, right? And I ask a question like, is that in the dual cone? No, because look, here's a point over here in the cone, and it's got a negative inner product with this thing, okay? So this is not, okay? Is this in the dual cone? Let's go slow. What I'm asking is does this vector have a non-negative inner product? Is it plus or minus 90? Is it within 90 degrees of every vector here? And the answer is it is. And what you figure out pretty quickly is that the dual cone is going to be this. It's basically itself. And then that has a fancy name that's called a self-dual cone. Okay? So this is the picture. Now, by the way, I don't think that you could get all of it now. So if you didn't get it all, not a problem. You will have many, many chances to get this later. Okay. Now, it turns out there's connections between minimum, minimal, and dual cones and things like that. And this is actually going to end up being super important in a lot of practical stuff that we'll see later. Actually, a lot of times you've already seen it, right? So in other contexts, right? So if a set over here, that's S, has a minimum point, in this case it's X, right? Then it's a minimum element if and only if, whenever you minimize lambda transpose Z over S, for any lambda in the dual cone, you get actually X, it says X is the unique minimizer of this, right? So that's actually kind of interesting. Let's suppose that the cone is the non-negative orthant, right? Then what this says is actually really interesting. If you are a minimum point of a set with respect to the non-negative orthant, it says that pick any positive weights, that's lambda, form this linear combination, minimize, and you always get the same thing. You always arrive at this minimum element, right? So that's what that means. It means independent of these weights. However you weight them, doesn't matter. You always get this minimum element, which kind of makes sense, right? Minimal elements, you can find these actually very nicely. This says you simply take any weight that is positive in the dual cone, and then you minimize this linear function over Z. And what happens then is you are guaranteed to get a minimal point. Now you've seen this in other contexts. This is like, when you're doing multicriterion optimization and you make a weighted combination and you minimize a non-negative weighted combination, you get something that's, Pareto optimal, which we'll talk about all this stuff later. There's a question.
What V?
What is what?
What is V here?
What is, I'm sorry, V. Sorry. Z. Is there some Z? Z is a dummy variable, right? So if I say this is a function, which is f of Z equals lambda transpose Z. So Z is a dummy variable, right? It has no meaning. You can change it to your favorite character. Yeah?
Can you explain what lambda means?
Well, lambda itself doesn't. Lambda is anything that is positive in the dual inequality, right? So it's any vector in the positive dual inequality. That's what it means. Okay? So again, this is kind of weird and out of context, so I wouldn't worry too much about it, but it's something we will see over and over again. Okay. And our first, like, baby childish application from economics goes like this. I mean, this is silly, but so I have to produce a product, right? And I have a production set. And a production set in general tells you, and you have different ways of producing it, right? And a production set in general tells you, it tells you what are all the choices that parameterize your production set, which is feasible, right? And so this is just a made up thing with, like, fuel and labor. I mean, it's silly, but there it is. And it said we can produce what we need to with any point in here. And I mean, we're getting a little bit ahead of ourselves, but we can talk about this. If we decide that, I mean, here I call them fuel and labor, but it doesn't matter. If we decide that each of these sort of has value, positive value, not negative value, then what that tells you is kind of everything down and to the left is better. Because it means, for example, let's see. If you took this point and you said, you say, thank you for your order. Here's how I'm going to run here's how I'm going to run my business. Okay, and you take this point. Anybody have a comment about that? What? Yeah, I heard the word. It's good. We'll get to it later. It's not efficient, right? So, or I'll tell you, the technical term for that is that would be a stupid choice. That's the technical term, right? Because you'd say, why would you run it like that? Like, excuse me, but this is silly. If you're going to do that, why not do this? And I can make the exact same stuff, and I'll use less fuel and less labor. And I don't know what they would say about that. And they'd say, yeah, but how do you know it's better? I haven't told you the price of fuel and labor. And you go, dude, as long as they're positive, this is better. Okay, everybody got this? So we'll get to all this. And you can see that these are just concepts of efficiency and minimal points. And one name for this is Pareto optimal. And again, we'll come back to this later in quite a lot of detail. But this is things you've seen, I think, or things you've heard of, maybe. Okay. Okay, now we're going to jump into convex functions. And first I'll just say what a convex function is. So a convex function it's a function from Rn to R. It's got a domain. That means that's all the points for which f is defined. That's the domain. Okay? And the domain has to be convex, and then it has to satisfy this inequality. And what that inequality says is, I mean, there's some weird terms, I forget what people call this, but this is the graph of the function here. And I think, this is called a chord, I think. That's like some ancient, comes from ancient Greek or something. So that's a chord of the function. And what it says is the chord lies above the graph, right? Or I like to think of it has non-negative curvature, right? It can have zero curvature, right? Then they would be like an affine function. But convexity means non-negative curvature. Or you could even say this. You'd say all convexity is we're talking about the sign of the second derivative. We'll get to that. But roughly speaking, that's what it means, right? Okay. So, and we say a function is concave if minus f is convex, right? That means it curves down. And a function is strictly convex if this inequality here holds strictly as long as theta is strictly between 0 and 1. Okay? So one way you could think of it lots of ways. This says f of the mixture is less than or equal to the mixture of f. So it tells you that when you commute a mixture and the function, you get an inequality always holds. Okay, so that's a very good way to think of it. Okay, so this is what a convex function is. Let's look at some examples. First, we'll just look at examples on R. Yeah, by the way, how do you check if a function on R is convex? You plot it, like in your head, basically. I mean, at some point, somebody would, I don't know, if you're being deposed by a group of surly mathematicians, I suppose you'd actually have to show it, and you can't draw a picture. But the point is, for an R, you just visualize it, and you can say, right? So the graph of ax plus b, it's a line, right? It's actually true that if you take the chord between any points on a line, I mean, it's silly, it's on it. Actually, what happens is, in that case, this holds with equality, right? So, okay. Here's one, exponential, and that's with a positive or negative thing. And we'll soon see ways you could actually prove this, but it's kind of silly. you just draw a picture and you'd say, look, here, I'll just draw you some functions. Ready? Here's one, and here's another. Okay? This is like e to the x. That shouldn't go below 0. That's e to the minus 2x. Or I don't know, I made it up. But it looks like that, right? And these they clearly have non-negative curvature, right? So those are examples. Powers. Well, a power's bigger than one work. And then powers that are negative work too, right? Because a power that's negative might look like this, right? Here's 1 over x, and it goes like that, okay? And then that's going to be convex, okay? Let's see. Negative entropy, right? So x log x, if I take a minus, that's the negative entropy. And that is a function that looks like this, right? Here's here's 0. Here's 1 where it's 0, and then it kind of goes, it's very steep there and then goes up like that. And it's convex, right? Or if you like, you could think of it this way. Entropy, which is minus x log x, is concave. And these are the kind of things when we start doing some statistics and other stuff, this is gonna kind of make it's gonna be very natural, okay? So these are some just simple examples. For concave, you'd have like the square root. There's your canonical concave power, right? But so is the 0.7 power. And the log, that's another famous one, right? Is going to be log. Okay, and don't worry, these are obvious, but we will soon get to ones that are not obvious. Okay, now we can have some examples on Rn. So if you have an affine function, so here the variable is a vector, right? And this is an affine function. And it turns out that's actually both convex and concave. Because I think of it this way. Convexity means non-negative curvature. Concave means non-positive curvature. If you're zero curvature, otherwise known as affine, right? Then you're in both, you're right on the boundary. You satisfy both. Any norm in Rn, any norm at all, but for example, the p norm would be 1, right? And if you haven't seen the p norm before, it's time. And if you have, that's great. You probably, certainly everyone here has seen the 2 norm or Euclidean norm, which is the square root of the sum of the squares, but you might not have heard about the 3 norm, which is the cube root of the sum of the cubes of the absolute values, right? So you might ask, like, what do you use that for? And the answer is, I don't know. But the 1 norm, that's reasonable, right? The 1 norm is the sum of the absolute values. That makes sense in a lot of applications, actually. And then the infinity norm is defined to be the maximum, right? But the point is, these are convex functions. That's actually the point here. Somebody has to show that, right? And we'll quickly see ways to do it later that are quick and painless. But technically, somebody has to show this, right? Okay. Now, we'll also look at functions sometimes on matrices. So that means that the argument of a function is a matrix, right? Like, for example, the determinant of a square matrix, right? Or the trace of a matrix or something like that. So we're going to look at things like that, or actually the norm of a matrix, okay? So, and here, it's interesting to know, what does an affine function on a matrix look like, right? Well, you know that an affine function on a vector looks like this. There exists a vector A and a scalar B for which the function has the form A transpose X plus B, right? Well, the analog of that for matrices is actually really interesting. It's this. If you look at this and you wrote out the formula for that, you'd see that they're kind of the same. It's a sum, a weighted sum of the coefficients, that's a linear function, plus a constant, right? And you can write that in fancy compact matrix notation this way. Trace of a matrix is the sum of the diagonal entries. And you can just check the trace of A transpose X. So when you see trace of A transpose X from now on, it's not some weird matrix formula. It's actually the inner product between 2 matrices, right? Should we just check that, or let's just check that, right? So if I have a matrix A and a matrix B, and I form this thing, trace, what I have to do is I have to add up the entries on the diagonal. Okay? So let's look at the 1, 1 entry of this matrix. Well, the 1, 1 entry of this matrix is going to be, it's the row of A transpose interproducted with, if that's a verb, interproducted with, it doesn't sound good as a verb. Anyway, with the first column of B. So I'm going to write A is like, well, it doesn't, I'll do that. Yeah, I'll write it out in its, I'll leave yeah, here, I'll just make these both n by n to make this simple, right? So it looks like that. So the 1, 1 entry of this matrix is actually A1 transpose B1. Okay? So that's what that is, right? Because it's the first row of A transpose, which is the first column of A, right? Interproducted with the first column of B, right? So this thing is going to be, you know, A1 transpose B1, and then I'm going to add up all the way to here, and I'm going to get that, right? And I could write this out entry-wise. This is simply sum over I and j, aij, bij, and that sure looks like an inner product to me, right? So, or if you'd like to say another way people might write it, is you might write it's vec of A transpose vec of B. This is not standard mathematical notation, but most people would know what you're talking about. Vec is some mapping that strings out the entries of your matrix in some specified order. Okay? So, or even worse, you could write this, right? And I don't know what that is, but it's evocative of certain languages I'm not even going to mention. Okay? But whatever, everybody got that? Okay, so these are just things you'll see before. Okay, so here's a function that's convex. Actually, any norm is convex. It follows just from the properties of a norm, but the spectral norm, right, or otherwise called the 2 norm, induced 2 norm, and it's this. It's the maximum singular value of that matrix. That's a convex function. Okay, so yeah. By the way, it's really. I mean, you can't write this out analytically if any dimension of x is bigger than 5. You cannot write out a formula for it, because you'd have to find determinant of x transpose x. Minus lambda I, that's a polynomial of degree at least 5, and there's no formula for the roots of that, right? Nevertheless, that doesn't stop people from using the 2 norm all the time, right? But the point is that function is really complicated and it's convex. Okay, so you'll see some others pretty soon. Okay, so here's a general method. It's useful sometimes for checking convexity. It says the following. If I have a convex function and I restrict it to a line, now restricting it to a line means I'm only going to look at its values along the line, right? A line in Rn. Then the restricted function is convex. Not only that, it's a function of a single variable. You could plot it and just look at it with your eyeballs and see that it goes up, right? So by the way, this gives you a completely reasonable way to check if a function is convex. If the methods we're going to talk about later today and next lecture don't work, then real simple. You generate random lines and then you plot the function restricted. And if every time that comes up, it's got positive curvature, you hit carriage return and go to the next one. I mean, this is not a very good way to do it. But if you ever see anything where it's got even the slightest non-convexity, then you stop and you announce that function is not convex, right? So, okay. So basically says it's convex if and only if it is convex when restricted to any line. And here's an example of this. This is a cool example. It has been known for more than 100 years that the log of the determinant of a positive definite matrix is concave. Okay, which is crazy. And it's a really complicated function if you think about it, right? It's the log of some crazy polynomial with n factorial terms in it. Everybody following this? Right? It's just like, how on earth would you know what that? Now, of course, we don't compute the log of the determinant that way, so that's silly. By the way, how do we compute the log of the determinant? We'll talk about numerical stuff later in the class, but how do you compute the log of the determinant of a matrix? I'm open to suggestions. Write out what the determinant is? No, that has n factorial terms in it. Okay, so how do you do this? Yeah, sure. Okay, you can compute its eigenvalues and then sum the log of the eigenvalues. Okay, and suppose you wanted an exact method that didn't involve eigenvalues. What would you do? This is just for fun. I mean, we'll talk about these things later in the class. You don't have to know it now. You'd take a Cholesky factorization of the matrix, and then you'd take the product of the entries. Well, you'd take the sum of the log of the entries on the diagonal, right? So, and that's an order n cubed operation as opposed to n factorial. And just for the record, n cubed is a lot better than n factorial. So, okay. So that was an aside, didn't have to do with anything. Okay, so let's see that, so this is actually saying something that's, I mean, you have to get some respect for this. That's like a really complicated function, right? And yet it's concave. Not only that, they knew this in like 1905, okay? So in fact, I think the term convex had only come in 10 or 15 years ago, like at all. Okay, so here's how you'd show that. So to show this, what I'll do now, by the way, if you knew information theory, you could show this because you'd say, well, I mean, that's the entropy of a Gaussian variable or something like that. And then you'd take two things, it'd be a mixture of Gaussian variables. There'd be some, information theory inequality, famous inequality that would tell you this, right? But that's kind of weird and complicated for normal people, right? So, so here's how you do this. You take a matrix here. I'm going to pick an arbitrary point x, which is going to be capital X because it's a matrix. That's going to be in the domain. And then an arbitrary direction v, which is symmetric, but not necessarily positive semi-definite, positive definite, right? So this, if I take x plus tv, that describes a line in symmetric matrix space. Everybody agree? So that's, I mean, we can pretend to visualize it, but that's what it is, right? So there's a line of, like a line of covariance matrices or so, however you want to think of it. Okay, and so we want to find out, is this convex with respect to t, right? Well, we can plot it, but that'll come up. It's correct. It's concave. Sorry, it's concave. And so the way you do this is here. I just take this matrix expression. I take x to the 1/2. I take x to the minus 1/2, x to the 1/2 outside, x to the minus 1/2 outside here. I pull it out both sides. This becomes an I. This becomes t times x to the minus 1/2 v x to the minus 1/2. That's this thing. So I get this. Then the two other terms, I get two terms which look like log-det x to the 1/2, each of which is 1/2 log-det x. Okay, so I end up with this expression here. Okay. Now I go to eigenvalues and I say, well, I can write this thing out if I knew the eigenvalues of this matrix, right? And if lambda are the eigenvalues of this matrix is symmetric, but it is not necessarily positive semi-definite, right? So anyway, I end up with an expression that looks like this. This is as a function of t. Now we're cool because we could quickly convince ourselves that log of 1 plus t lambda is concave for any, for no matter what lambda is, right? It's concave, right? And then this is a sum of concave functions. We'll get to that. That's going to be concave, and that's how you do it, right? So that would be that. But this is already a not totally obvious thing, right? So, and in fact, I guess in a lot of classes, people would end up showing this by some very long convoluted thing or something like that. It's fine. Okay. Okay, one more thing we want to talk about with convex functions is they actually extend very gracefully. There's a way to handle the infinity, the domain very gracefully. And the way that works is this. What we do is you have a convex function f, and what we do, and let's just talk about f for a minute. So I have a convex function f. If I call, I'm going to use a dialect of maybe kind of street fighting computer science or something, but if I call f with an argument x that's in its domain, I get a number like minus 11. And that's what it is, right? Okay, that's cool. If I call f at a point outside the domain, well, it depends on who implemented the function, right? But maybe everything dumps core or something like that. But what should happen is you should get a return value that's like OOD, which means out of domain, right? But if you call it a couple of times, you should get OOD and then a nasty message, which is like, you're on, watch out. You do that 10 more times, and your privileges for evaluating this function are revoked, right? That's how that should work, right? So you should get something like out of domain, right? Or NA or NaN or whatever you like, right? Okay. So it turns out what you do instead is I'm going to define a new function, f tilde. It's going to be defined for everything. And I just, if you're out of the domain, you just call yourself infinity. That's it. And actually, what you're going to find out is that that inequality works. You can figure that out in your head. And everything just works, right, with this. And actually, it's kind of nice because it means a lot of times we'll work with functions that can have values of plus infinity. And those are just like, that's a way to, we'll see, to express constraints, right? That's how that's going to work. Right? So, okay. So it's just bookkeeping, but it does work. I don't think like, whatever IEEE 488 thing, I don't think it supports this. Actually, I should check if it, it actually does. They do have things like +inf and -inf and stuff like that. Whether or not people, when they write stuff for convex functions, actually support those things, it's another question. I don't really know, but okay. So, all right, so that's the extended value extension. Okay, now we get to some conditions. These are the traditional ones, and they're based on, tradition, which is our multi-hundred-year tradition of calculus, right? And so it's actually super interesting. Like, the gradient of a function. By the way, this construction here, a lot of people use different notation, which I despise. I don't. I use just one fixed notation. And to write a vector, you have exactly two choices. You can write it like this, right? A, B, C. That's like a vertical stack. Or you can write it this way, right? So the parentheses, for me, the parentheses and the comma is the constructor for a vector. Yeah?
Is our convention that the gradient's a column vector?
That's correct. That's a column vector. That's right. That's exactly right. Right. Okay, so that's the gradient, right? By the way, people write all sorts of other, the problem is people are programming in lots of different languages and they start writing things like this, right? And they start writing, I don't know, right? And they start writing all sorts of weird stuff. I understand what they're saying, but I judge them. Okay, so I just make a little note, like, and even worse, like in the same paper or talk, you'll find these two, and then they really get judged. Like, okay, so that was just a quick notation comment. Okay, so the gradient is just basically the set of all partial derivatives. And you should recognize this as the first order Taylor approximation of f developed at the point x. Okay, and what that means is this function here is affine. It's linear plus a constant, number one. And number two, at the point x, it's actually correct. It's actually, this thing, which you might call f hat, is actually equal to f when you plug in y equals x, right? That goes away, and that's just f of x, okay? So what calculus tells you is this. It says that this function here is really close to this function if y is close to x. But when I say really close, I mean like close squared, right? That's what I meant when I said that, right? So it wasn't just the English intensifier, right? Okay, so what this says is actually super interesting. It says, and this picture actually is related basically to kind of the entire course. What this says is that the first order Taylor expansion for a convex function, it's from calculus, right? In 1770, we knew, the notation would be different. We'd probably be writing in Latin. But we knew that the Taylor approximation was really close if the argument of if you're nearby the point at which you develop the expansion, right? That's what you know in 1770, right? But what we know is actually really cool. It says that basically it is a global lower bound or underestimator. Okay, so that's what it tells you, right? And I think this picture, if you have this picture in your mind, you're good to go. And I've had and in fact, in some weird way, like all the weird stuff in the class comes down to this one picture, which is really dumb, right? So what it says, so if you think about calculus gives you it's a local statement. It says this approximation is really close to this thing if you're nearby. And then you start saying like, well, how close do you need to be? And you're, oh, that depends, and blah, blah, blah. Okay, and it gets complicated and vague. Everybody, that's calculus, right? This is different. This says, no, we have just a global lower bound. It's always that way, right? And so actually this is going to come, because I remember once I was talking to somebody about, it was circuit design. We were talking about something, and I said, well, that's the best circuit design. The person looked at me and he said, how could you possibly know that? It's ridiculous, right? How could you possibly know that, right? What kind of, hubris? What would make you say that, right? I was like, because it's true, man. It's just true. And then he looked at me and he said, why? How could you say that? And I said, and it just comes down to this, right? So what it says is that when you have convexity, you can make global statements. In calculus, you make local statements, right? If I'm minimizing a function and the gradient is 0 or something like that, I can say, yeah, totally. If you move a small amount in any direction, the function's going to go up or something like that. You see what I'm saying? But you have no idea that there's not some place, some other neighborhood you haven't ever seen before where the function is smaller, right? For convex functions, that can't happen. Everybody got this? So roughly speaking, it says that from local information, you actually get global inequalities. I know it sounds like I'm making a big deal out of it, and it is nothing, but to be perfectly honest, this is the point in the whole class, right? So, I mean, not that you care about this, but you will later, by the 6th week, you'll be solving problems and saying, yeah, that's the best, right? And you don't even think about it, because you'll have optimized a problem with a couple thousand variables. And I got news for you. Our couple thousand is a really big place. And that's a very strong statement when you say, yeah, I just minimized it and the optimal objective 3.1. Someone says, what does that mean? You go, it means any other x you pick that's feasible is going to have an objective function greater than 3.1. That's what it's saying. And if you think about it, that's a crazy statement. And someone would say, how could you say that? Anyway, it's just because of this. You could mumble something about, well, for convex functions, from local statements, we can actually assert global things about something. Anyway, okay, I'll stop because it's just getting weird and ranting. Okay, so we'll just move on. Okay, next topic. Second order conditions, right? So if a function's twice differentiable, then its Hessian is a symmetric matrix, which is the set of all partial derivatives, right? And it turns out, and this makes these are very simple things to show. It turns out a function is convex if and only if, assuming it's twice differentiable, assuming that, then its Hessian has to be positive semi-definite at all points. And this makes total sense, right? Roughly speaking, if n was 1, you'd say if a function is differentiable, f prime prime is non-negative, right? So that's how you could, now you could do things like someone walks up the street and says, show me that the entropy is minus x log x is concave, right? So you differentiate it twice and you get something and say, there, see, it's always non-positive, and you say therefore it's concave. So everybody got that? So this is okay. Yeah. Okay, so this is the idea of, and it kind of fits, it makes perfect sense. Oh, and by the way, the Hessian is a measure of the curvature of a function, right? So this is it's cool. It kind of tells you, it's kind of cool. It tells you that, if I give a matrix or, whatever, you could be pedantic and call it a 2 tensor or something, and someone says, well, what do you mean, the function curves up? And you mean, its curvature is non-negative. And, if you had to make something up about what that means, it means that. Okay, so that's the picture. Okay, again, these are actually really easy to show. So I'm not going to do that, but it's a good way to just sort of start thinking about these things. Okay, so let's look at some examples. The first one, here's a quadratic function. So here I have this is a quadratic form, right? It's x transpose px, where p is symmetric matrix, right? By the way, p is not symmetric. I can replace it with its symmetric part, which is p plus p transpose divided by 2, and now it's symmetric, right? And it doesn't change this function, right? So that's a quadratic form. If you add to a quadratic form a linear term and a constant, you get a quadratic function, right? So this is the analog of basically px squared over p over 2x squared plus qx plus r in dimension 1, right? So that's what this is, okay? Well, the gradient turns out to be px plus q. And then it turns out that the Hessian is just p. It's constant. It has constant curvature. So you'd say, well, it's silly. You'd say, a quadratic function has constant curvature. Well, duh. That's kind of what it means, right? And then it turns out if this matrix P is positive semi-definite, this thing is convex. And that's if and only if, right? Here's one, least squares objective, right? So here I have a matrix A, doesn't matter its dimensions, except this has to make sense, and a vector B. I form this thing, and if I expand it out, the gradient is this thing, right? This is what you'd see in the normal equations, so-called, right? And then the Hessian is 2A transpose A, positive semi-definite. So it's done. Okay? So these are just good things to know. Now we get to a fun one. So this is the simplest convex function that most people are utterly unaware of, right? If I walk up to a person, okay, it depends on the neighborhood, but if I walk up to a person on the street and say, hey, is X convex? They're like, duh, of course it is, right? I mean, because you just draw the picture in your head. You know, most people would know that like a norm is convex because it's kind of like the triangle inequality, right? These are kind of obvious, right? Here's a super simple one. The function x squared over y, two variables, y is positive. Okay, so that's it. And it's not obvious that there are some obvious things. Here, if I fix y, it's convex in x because it's a positive multiple of x squared. If I fix x, it's convex in y because it's a constant 1 over y, and it looks like this, right? So it's convex, right? This says much more. This says it's actually jointly convex in x and y. Okay? So, and you know, you can check, I mean, but here's a quick one. I worked out the Hessian for you and expressed it as a rank 1 positive semi-definite matrix. That's what this is, right? By the way, the interesting part about the function is because it has rank 1, that means that wherever you are on the surface, it's actually got one direction where it's flat and one where it's curving. But there was a question.
Is the converse true if a function is jointly convex? Does that mean the individual variables are also convex?
Yes, but let me be very careful to make sure. So there is something in there that's false and very important. So let's get to that. If a function of two variables is convex, it is definitely convex, in fact, by our thing, by restricting it to a line, right? One line is just that the first variable changes and the second doesn't, right? So yes, if a function of two variables is convex, then if you fix one variable, it's convex in the other one, and vice versa. Okay? The converse of that statement is false. It is not true. A function can be convex in each variable when the other is fixed, right? Somebody want to give me an example? Like simple? Okay, a saddle. Yeah, here. Okay, yeah, that'll do the trick. But let me, you know, maybe it depends which directions you move in a saddle, but roughly. Here's one. Ready? Here's a function of two variables. Ready? That's the product. That's a quadratic form, right? This is equal to, right? Well, okay, that's equal to xy transpose times maybe 1/2 and 1, 1, 0, 0. Everybody agree with that? Okay, so that's my function. Okay, now, in your mind, please fix y and tell me if this is convex in x. It's linear. Now, in your mind, fix x, please, and tell me what is the curvature in y. It's linear. So it's convex. It's both convex and concave, right? Is the function convex? Well, its graph is a saddle. I think you'd suggested that, right? So that's how you know it's not. But the other thing is, well, wait, we just looked at this. I mean, the question is whether this matrix is positive semi-definite. Is that matrix positive semi-definite? No. I sense that our intuition about positive semi-definite matrices is not well enough formed. I just have a sense here. Like, how would I look at this and know that that's not positive semi-definite? Why? Yeah, okay. We can do eigenvalues. I mean, I happen to know the eigenvalues of that matrix. Do you?
-1, I think, is one.
Okay, -1 and 1, and it's game over with -1. There was a suggestion back there?
I actually can't read that matrix from back here.
Oh, I'm sorry. Yeah, that would make it very difficult. Yeah, you know what? I'm looking at it now. Thank you for bringing that. Oh, by the way, also, if you can't hear me back there, then let me know, because I can be loud. Okay, you're right. I don't know what. So thank you for some feedback there. Let me just read. I will now write it legibly, right? There we go. Can you see that? Okay. Is it positive semi-definite? It's not. Yes?
I seem to recall a property that don't the diagonals have to be greater than every other.
There you go. That'll do the trick, right? that at every point in every element of a positive semi-definite matrix is less than or equal to the geometric mean of the associated diagonal elements. Everybody remember that? Or okay, apparently not, but that's fine. Everything's cool. Okay, so and here that would say 1 better be less than or equal to the square root of 0 times 0. That's not true, so that's not positive semi-definite. Okay. Okay. So I think we said about anyway. So that's kind of it. It's an interesting function. There's a graph of it over there. Okay. Log-sum-exp. This is an interesting one. This comes up in tons of fields with completely different names. Every field thinks they invented it. So I think it's called Softmax in some fields. It's got, okay, somebody give me some other names. I know some weird esoteric ones. Want to hear a weird esoteric one? Okay, and this is in full dialect. So, what is it? There you go, Boltzmann function. That's kind. Is that? I didn't know that. The Boltzmann what? Okay, great. I mean, that's highly pedantic. Okay, so this function here's one from here's in a strong dialect. This is the dB combining formula. That's from EE. You may have friends, or you may at some point in your life have friends who are in EE. So probably worth your while to speak a little bit of the dialect, or at least recognize when people are speaking it. Okay, so decibel is some weird thing from the 1920s. It's like the 220 times log base 10 of a function. Anyway, so it turns out that's the formula. So I will, if you don't mind, I'm going to go into full EE. And you'd say, if you walk up to any electrical engineer and you say, well, I have all these, I have these powers coming in. I have this one coming in at like, minus 11 dBm. One is coming in at plus 13, one at 14. And if I add up all the power, what's the total power? And they would know. Okay, so that was weird. By the way, does anyone speak that dialect? Somebody does. Okay, we have one. Just you speak a little bit? Okay. Did you grow up speaking it like at home or something, or what? You did. Okay, fine. Okay. So I know other dialects. I can try that. Okay, fine. Okay. So it's actually a really cool function. Okay, number one, it's convex. Which, I'm not going to go into the details, but the reason you figure that out is actually, it's an interesting derivation. It goes like this. You work out the Hessian. It's a sum of two terms, and you look over here and you'd say, well, let's see, it's kind of, so Z is this X, so these are non-negative, right? You'd say, well, I don't know, that's a positive semi-definite matrix. And then what you're hoping, the simple thing would be, the Hessian is one positive semi-definite matrix plus another. And then you'd say the sum of two positive semi-definite matrices, but it's not to be. There's a minus sign here. And this is this rank 1 thing. It still is positive semi-definite. You have to show it, which I'm not going to go into the details here about how you do that. But anyway, so this is, and it's a very cool function. It's actually basically like, I think, I like Softmax. I don't know who invented that, but maybe, I don't know, maybe people in machine learning. I don't know. So that's my preferred term for it. Softmax means it's kind of a smooth approximation of the max, right? Like, I mean, if you've seen this before, how many people have seen this before somewhere? Yeah, so, okay. So, it's like, look, if one of the x's is let's say a factor, not a factor, but let's say it's even one x is like bigger than all the others by let's say a gap of 3, right? Then it's, when you exponentiate them, it means that one is now more than e cubed bigger than all the others. So when you add up the others, I mean, it depends. I'm just being very rough here. Most of it comes from that one term, right? And then you add them up, you take the log, put you back on the other scale, and you get that. So, okay. Here's another one, is the geometric mean in many variables. So the nth root of a bunch of positive numbers or non-negative numbers, that's a concave function. And you'd have a similar thing, right? So, okay. So let me briefly mention the connection between convex sets and because right now you have the convexity now applies to two things. You have convexity of a set and you have convexity of a function, right? And so, obviously people would not have used the same term if there was not a connection, right? The connection might not be quite what you think it is. Oh, by the way, we have concave functions. We don't have concave sets. No such thing. I mean, you could say that, but it would be weird, right? So I'm not even sure what it would be. but maybe the complement of a convex set, or I don't know what it would. Actually, I don't know what it would be. So don't say that because it has no meaning. Yeah. Okay. So there's a connection between these things. So the very important one is the concept of a sublevel set. Now, a sublevel set of a function is the set of all points where the function value is less than alpha. That's actually super interesting, right? When f becomes an objective in an optimization problem, this is basically, these are all the things that perform at the level alpha and better, right? Because I'm minimizing f, let's say. Okay, so that's the sublevel set. It makes perfect sense, right? Or you could have like the super level set, something like that, right? Okay, now it turns out that the sublevel sets of convex functions are convex. Okay, so if you have a convex function and I look at the sublevel set, it's going to be convex, right? So, okay, let's see. The real connection is through the so-called epigraph. Epi means above, graph means, I guess, just graph, right? Which means a drawing or whatever. And so remember that if I have a function on Rn, its graph is a set in Rn plus 1. It's a set of all points of the form xt, where, x is in the domain, and f of x equals t. That's actually the graph, right? The epigraph is everything that lies above the graph. And so this is a function f. This dark curve is what we'd call its graph. It's in, here n is 1, so it's in R2. And the epigraph is this shaded thing. That's the epigraph, okay? And it's kind of interesting. It's everything that's bigger than or equal to the function value at that point, right? So that's the epigraph. And it turns out a function is convex if and only if epi f is a convex set. So that's actually the connection between the concepts of convexity of a set and convexity of a function. Okay? So, it's not that much here. But yeah, we're already getting close to interesting things. So let's fit a statistical model by minimizing the negative. If you understand what I'm saying, fine. If you don't, that's cool too. We'll do this later. Let's fit a statistical model. X is going to be the set of parameters in your model. And I want to minimize the negative log likelihood. Everybody following me? It's fine if you don't, right? So, okay. And you would get something, and that'd be like the maximum likelihood estimate of those parameters. Everybody cool? Okay. But then I could look at the sub-level sets of the negative log likelihood, or if you like, the super level sets of the log likelihood. Okay? So again, if you're trained in statistics or probability, if you know what I'm doing, that's fine. Those are actually super interesting things, right? Those are the sets of parameters for which your log likelihood exceeds some minimum value. And if that's near the top, right? So you would get something like this, right? Here's a log likelihood, right? This would be the maximum likelihood point. The super level sets are super interesting. Like it's these points here. And they would have a beautiful statistical interpretation. Because if you're close to the maximum likelihood, then it would be very hard for someone to say your model is different. In fact, if you were to actually try to figure out like which hypothesis was correct, is it this or is it that point? You could actually talk about how close they would be. Okay, so it's already getting kind of. By the way, what are the if you take this is just for fun since I started on this weird thing, but that's the maximum likelihood point. If you just back off tiny bit from the maximum likelihood, what do those super level sets look like? Just for fun, if you're in statistics, and I know there's people in statistics here, so and you should even know this if you're not in statistics. So what do they look like? What are the sets of parameter values that are almost maximum likelihood? Yeah. They're what?
Confidence intervals?
Yeah, they're confidence intervals. Yeah, but I'm talking about in many dimensions. What do they look like? What's their shape? They look like ellipsoids, right? They are indeed confidence intervals. They look like ellipsoids. And in fact, the curvature is given by the Fisher information matrix. Okay, so sorry, that was too weird, but I shouldn't have done. I couldn't. This stuff is so boring and dry at this point in the class. I can't help myself, so I apologize. That was just a weird thing. Okay, so fine. We'll get back to that later. Don't worry. Okay, so Jensen's inequality. Jensen was a mathematician who kind of popularized the concept of convexity about 120 years ago. I mean, basically, actually, people had all these sort of inequalities known, and they used them to prove all sorts of things. All he did was kind of codify it. And he said, hey, I just realized that these 14 different people are using the same argument, and so I'm going to introduce a concept called convexity and an inequality. So, okay, so here's Jensen's inequality. Jensen's inequality is just the inequality that defines a convex function. It says a function at the mixture is less than or equal to the mixture of the function values. This is so-called Jensen's inequality. Well, the extension is you can extend this all the way to expectation, and it would go like this, right? Suppose z is a random variable, then its f of expectation is less than or equal to the expectation of f of z, right? For any random variable. And by the way, this is a special case of this where I just have the probability. I just have z is concentrated on 2 points. It's either x or it's y with probability theta and 1 minus theta respectively, right? So that's Jensen's inequality. And actually, it's a super interesting thing. It basically tells you, let's see. Okay, so I might think of it this way. You could say that dithering hurts, or actually risk hurts. So let me just draw a picture of that. And this will get clear later in the class when we do other stuff, but let's just try this out. So here's a convex function, right? And then I make a little probability distribution that looks like that. There. This is x here. Here's my little probability distribution. And I want to know what happens to what happens over here to the, if this is x and this is like, let's say y equals f of x, right? I get a new distribution on y, right? Looks like, I don't know, looks like that, right? Okay? And now let's do some calculations here. What it says, let's suppose that x is actually this nominal value plus something that's zero mean, that wiggles like that, right? Well, what you do is if this were affine, like that, we all know what happens to a random variable when you pass it through an affine function, right? Like variance maps the right way. But the super interesting thing here is now what we're doing is sometimes we're above, sometimes we're below this value. But what convexity says, or at least if you understand what it means locally, it says that if you're above or below, I mean, there's the affine estimate of what happens to you, but you're always worse than, you're always larger than that, right? And so then this thing makes perfect sense, right? That you have this value, but you wiggle around sometimes. And that says you have this value here, but you also wiggle around that. But when you wiggle around like that, actually, it always goes up, because even if you go down here, you're above this line, and if you go up, you're above it too. Okay, so maybe that didn't make any sense, but that's just my interpretation of this. So this is just a very basic thing. It's Jensen's inequality. Okay, so at this point, let me explain a few things about how this is all going to go down. And this is actually sort of the beginning of how we move towards something reasonable, right? If this were a math course, we could just go for the rest of the quarter, and I could show you interesting convex sets and go off on weird tangents and stuff like that. That would be which would be fine. No, it wouldn't actually. But anyway, so the way we're going to do this is we're going to do this like it's going to be a calculus, right? Oh, and by the way, it's not just the right way to think of it mathematically. It's going to turn out this is also what makes this 100% actionable in code. So everything we're about to say is math, but it's actually going to be backed up in code, and it's actually going to be the key to a whole lot of stuff. Okay, so let's go over these things. How do you find out if a function is convex? Well, every now and then, extremely rarely, and you should do this only if you're absolutely pushed, if you have no other option. It's basically, okay, let x be in the domain, let y be in the domain, let theta be between 0 and 1, f of theta x plus 1 minus theta y, and then a lot of math and argument and stuff like that. So don't do that if you can get it, if you can avoid that. Okay. If it's twice differentiable, you can compute the Hessian. Okay. You know what? Don't do that either. I mean, unless it's something super simple, right? But generally speaking, that's not the right way to do it. I mean, it is like for showing like log determinant or something. That's a bad example. So log determinant is a really good example. right? So if someone says show log determinant is concave, you go, not a problem. All I have to do is calculate the Hessian of the log determinant with respect to a matrix. Everybody following this? Well, okay, matrix already has two entries, two indices. It's indexed by I and j. The Hessian is indexed by 4. That's I, j, k, l. Okay? Now, in my experience, the only people who are actually able to actually work with tensors, like things with 4 indices, are people in like mechanical engineering, right? So they can do it, right? These are like weird stress strain tensors. Some physicists can do it, or at least they say they can do it. But honestly, normal people can't do that, right? And how on earth would you write down some crazy, I said, well, show me my 100 by 100 matrix is positive, same. You go, let's work out the Hessian. There's 5,000 entries, so it's a 5,000 by 5. Anyway, it just gets very unattractive. Everybody following this? So, okay. All right. Okay, this is the right way to do it. And it's a calculus. And the way you do that is we will have a bunch of atoms, things that we know are convex functions. Here's one, log is concave, exp is convex. Log-sum-exp is convex. Log determinant is concave, right? So you're going to have these things. You're going to have, there's not that many of them, right? 20, 30, 50, I don't know. It's not that many. You will know all of them. You'll know a bunch of them, right? And then you're going to learn calculus rules, which is how you combine these things, right? And so, some of these are going to be mind-numbingly simple. Like, here's one. The sum of two convex functions is convex. Well, first of all, it's obvious. Draw a picture in your head, draw a function that goes up, another one goes up, add them together, it still curves up. Like, hello, of course, right? So anyway, that's one. But, some of these are going to be, we're going to see some very interesting ones that are not obvious in some of these rules. Not only that, it's going to turn out that at least all these 4, which we teach as separate rules, it turns out weirdly, they're all the same rule, which we'll get to. Not only that, it's the main rule behind constructing code where you can verify a function is convex or concave, which we will get to later, and you will be doing in about 2 weeks. Okay, so this is the program. It's constructive convexity analysis. That's what this is, right? So, no gradients are harmed in the proving of convexity, right? Which you don't want to do anyway. Right, and no one is going to you're not going to go back to the basic definition. Okay, so we'll look at a couple of these and then we'll quit for today. But this is the point at which it'll start transitioning to something that you can that's actionable, right? So, okay, so we'll start simple, right? Here's one. 3.7 times a convex function, that's convex. Well, okay. Whatever. Like the curvature just went up by 3.7. If it was non-negative before, now it's even more non-negative, if that makes any sense, right? Which it doesn't, but okay, that's fine. Okay, the sum of two convex. And by the way, somebody has to prove these. These are like one-liners. I'll tell you when a couple that aren't one-liners, but these are one-liners, right? Here's one, pre-composition with an affine function. So if I have an affine function, that's ax plus b, and I take that, and then I pump it into a convex function. This is a function of x, and it's also convex. And that's not hard to show. It kind of makes sense, right? Okay, let's look at some examples, okay? So this function is going to come up later in the class. It's called the log barrier. Its domain is all x's for which all of these numbers are positive. Otherwise the log doesn't mean anything, right? Oh, in this class, the domain of log is r++, right? So if you're taking a class on complex analysis, that's not true, right? So it just depends on the social context. But here, when I write, log determinant, log, that's what it means, okay? So, okay. So here, this is the so-called log barrier of a set of linear inequalities, right? And all the inequalities have to be strict. In other words, you better have AI transpose x less than b. Otherwise, this log doesn't even make sense, right? And so that's the log barrier. And it turns out that's going to be convex. It's got a minus in front. Why? And the rule would go something like this. Well, let's see. This is affine function with a concave function, right? And then concave of affine, I'm saying it the way you will say it, and you will think it by week 3. This is the way you will think. You'll say concave of affine is concave. okay? Then sum of concave is concave, okay? Minus converts concave to convex. Everybody following this? Okay, so you will be doing this without even thinking. It's going to be like parsing English syntax. This is how it's going to work. And we're going to talk at very high levels, and you're going to say things like that, and not even, that's the way it's going to work, right? Okay, so I think what we'll do is we'll quit here. We'll finish this off next time. And by the end of next lecture, by the end of this week, you will have survived, maybe. We'll see.